Hello, Mr. Collier here. This is the second lesson about electrons, and I want to talk a little bit more about some of the more complicated theories that go with electrons. So, I mentioned that electromagnetic energy moves at the speed of light, which is 3 times 10 to the 8th meters per second, or just to give you another frame of reference, that's 186,000 miles every second. Incredibly fast. And the relationship between wavelength and frequency can be shown as follows. Wavelength is equal to the speed of light over the frequency. In other words, they are indirectly related or inversely related. So as the wavelength goes up, the frequency goes down. They're inverse. Photons of light have a dual nature that is very interesting and complex. They travel through space like waves, which I talked about in our last lesson, but they also act like particles when they interact with matter. I'm going to show some videos in class that help to understand this concept. So for example, particles would produce straight shadows when they hit a barrier, but waves would bend around a barrier, and light does just that. Light bends around things. Max Planck in 1900 noticed that an object absorbs or emits light in little packets or bundles called quantum, or quanta if you're pluralizing it. And energies are quantized. Think ramps, not a step. So you can have electrons that exist at certain energies, like they're on certain steps, but not in between those. This is what we mean when we say quantized. On a step, not on a step, nowhere in between. And he came up with the equation that relates energy to the frequency. And he came up with something called Planck's constant. Not something you need to memorize, it will be given to you on tests. And energy is related to the frequency. This is a direct relationship. So higher frequency waves have more energy. So a quantum of light is called a photon, and light travels through space as waves, but it acts like a particle when it interacts with matter. This is that dual nature of light. Now, what this allows us to do is look at light given off by individual atoms. An atomic emission line spectrum contains only certain colors or wavelengths of light. Every element has its own line spectrum, which we use as a fingerprint to identify that specific element. We actually do this in a lab in this class. So you can see different elements giving off different characteristic wavelengths of light. A continuous spectrum given off by white light contains all the different colors, but individual elements will give off just certain wavelengths which will show up as lines when you look at them through a spectroscope. We can use gas discharge tubes to figure out what elements are in them by looking at the light that is given off. A spectroscope is the piece of equipment that we use to identify these different wavelengths. It is basically a piece of plastic with a prism on the inside. So Bohr came up with a model of the atom that said that the energy of electron was quantized. They can only exist in simple, certain orbits that represented different amounts of energy. He labeled each energy level with a quantum number. So N1 is the first energy level. It's the lowest energy level. It's the ground state. When electrons absorb energy, they jump to a higher level. We call that the excited state. And when they fall back down, they emit light. This is what all the emission line spectrum comes from. Here's a diagram showing that as an electron falls from a higher energy level back to a lower energy level, it emits light. Think of it as a basketball bouncing downstairs, and as it bounces, the sound that a basketball makes is kind of equivalent to the light that an electron gives off. So just for one specific example, when you're using a hydrogen atom, electrons that fall all the way to the first energy level give off ultraviolet light. When they fall to the second energy level, they give off visible light. And when they fall to the third energy level, they give off infrared light. Werner Heisenberg was a scientist who came up with the uncertainty principle, stating that you can't know both the position and momentum of a moving object simultaneously and exactly. So that means you can't accurately predict future locations of these particles. With this, he found a problem with the Bohr atom. There was no way to observe or measure the exact orbit of an electron. This leads us to the quantum mechanical model of the atom, which combines a lot of the previous ideas and treats the electron like a wave that has quantized energy. It's impossible for us to state the exact position or the momentum of an electron, but you can state the probability of where that electron will be located. It's very complex, and we're going to watch some videos and discuss more in class.